Good morning, everybody. Today I would like to talk to you about a study we did some time ago and wrote a paper last year on it. The purpose of this study was to build a model to allow for quick and easy estimate of the amount of steel to be utilized in constructing fixed roof oil tanks. Uh, Though it was specifically done in the oil industry, the model itself can be applied as well to other industries with certain considerations, of course. That said, let's move on. So in the paper and in this presentation, we'll cover three large parts. First, we'll briefly go over what kind of tanks we have considered. Then we'll go over the work we've done on modeling these tanks. And lastly, we will test the model on real-world tanks that we collected from several operators and EPC contractors. So first of all, these type of structures are found in the oil and gas in two main areas. The first one is to store the liquid products, namely oil condensate and water separated. And it can also be utilized in the process, namely for the emulsification of oil and water. In literature, there are many ways to categorize different tank structures, and there are multiple ways to divide them. Here we see what I consider a quite comprehensive categorization of tanks, and what I wanted to outline here is what we're dealing with. So we're focusing on the above ground storage tanks with a single wall structure, a flat bottom with atmospheric pressure. This is very important because different codes apply based on the pressure, and a fixed roof, specifically a cone roof, either self-supported, center-supported, or just a cone with multiple columns supporting it. There are other tanks that are utilized in the oil and gas industry, but they are not investigated in this paper. Namely, that would be the floating roof tank, which is utilized in the oil and gas industry quite extensively. However, we have not considered that in this paper. In terms of the industry codes, two most popular codes utilized in the oil industry are API standard 650 for the welded tanks, and API standard 620. If you remember, there were two. There was atmospheric pressure tanks in the previous slide. That's where the 650 applies, and there were low pressure tanks, and that's where the 620 applies. Albeit these two codes are the most popular ones in the oil industry, to make the model more applicable to other industries as well, we have utilized Euro codes in design of our hypothetical tanks. So we're focusing on the cone roof storage tanks. Here we see a schematic of one such storage tank, as well as how they are constructed. Usually welded on site if they are of larger volumes. The tank shell is made up of plates that are welded on site and bolted to and welded to a tank bottom, which is further bolted to usually a ring type foundation or a circular foundation, depending on the actual application. So the three main elements of these tanks are the tank shell, which carries most of this weight, steel weight, tank bottom, and the roof. So here the goal here was to identify how does the steel surface utilized, and therefore the weight utilized, weight of steel utilized, behave with a selection of different diameter and height ratios, This ratio is quite important, and we'll be coming back to it multiple times during the presentation. All in all, as expected, when we're talking simply about geometry, the optimal DH ratio is 1. Same applies to weight, but as we select thicker and thicker shells, so does the DH ratio move from 1 to higher values. What's also important to consider is that the weight of steel utilized is comprised of different elements. And in this work, we are focusing on 3 main ones: shell, bottom, and roof plates, out of which bottom and roof plates are more or less fixed by the standards, so they will not change as much with the design. Shell, on the other hand, however, is very much affected by different design parameters as specified in the basis of design. Roof support and such as columns and beams and other opportunities like pipes, vents, manholes, they comprise from 10 to 20% of the total weight, and in this paper they are considered by an empirical function rather than designing them for each tank separately. So with that, I'll proceed to what we did with the regression modeling and how it applies to the real world. So what we did, we wrote quite a long design algorithm for a sample of 430 tanks, and then considered different values of the diameter to height ratio, the specific gravity of the liquid, different steel strengths, seismic hazards, volumes, etc., etc. And the output of this model was that so out of all these 432 tanks, the minimum shell thickness would be a 6 millimeter, that's more standard driven, and the maximum would be 16. And then the steel weight would vary from 35 to 380. Of course, that's mainly driven by the volume, but as we'll see, it's also driven quite extensively with the DH. When we look specifically at the shell thickness, we've considered several different regression models, and we've determined that this specific model, Model 4, is the one providing most stable and reliable results. As we can see, the bulk of this estimate lies in the -10, +10 variation from the median. Same applies to the weight. So for the weight, we took the modeled thickness, average thickness of the shell, and applied it in a simple weight calculation using geometry. We also introduced the modification function, which further modifies the weight to account for the items that were not accounted by this model. If you remember, I said that the roof support, columns, beams, opportunities, they're not included, they're not covered by this model. So what we did, based on the real world tanks that we collected, 21 in this case, we have estimated for different capacities and diameter to height ratios, what is the total, how much does the roof support and the opportunities figure in a total steel weight, and then we modify that number with this function. So here we come to a final model that was built using the data collected as output and running it through an R software, statistical data analysis software. And the main function here is the one for determining the average thickness, so the weighted length, height weighted average thickness of the tank shell. Once we determine that, that goes into the weight formula, determined by the geometry of the tank. And once we calculate this part of the function, we modify it using the fmod function, which, as I said, figures for other things that are not covered by this model. And the fmod function determined as per the real-world tank data is contained here. So one additional thing we did is we wanted to see, well, what if we give based on the functions we selected, what if we give random data to our model? How stable will it be? Will it throw data around, or will it give smooth curves and something that can be further extrapolated? And these were the results of that exercise. And lastly, as I said, so finally we wanted to test this model that was built to replicate real-world data. And we collected a total of 32 tanks. However, of those 32, 21 were fixed roof. We collected them from different operators and EPC contractors that were willing to share the data. They contain different products, different locations, different standards used. There are tanks here that were built in the 70s, in the 80s, in 2000s, fairly new ones as well from 2015, 16. Sorry, 12, 13. So it's a very varied data set. Once we overlay the data we collected and try to determine how much does it deviate from what we would expect to see by the model, we see that the bulk of the error for determining the average shell thickness is around 10%. At the same time, the bulk of the error for determining the weight is also in the 10% range. So it looks like the model does good prediction. However, there are a couple of fairly big outliers, some going even to the 50%. And we did an analysis on those outliers and figured that some of the data we collected is incomplete. In some cases, water tanks were analyzed, so not oil tanks, and usually these have higher corrosion allowance, especially if they're separated from the oil. In some cases, tanks were quite old and used different standards, like in case of Hungary. And also higher specific gravity liquid was contained within them, along with the higher safety factors. So that was a brief overview of the paper. I hope you enjoyed. Thank you very much for listening, and have a nice day.